So I realize what you see in front of you makes you want to cry real tears to get this video started. I would not blame you if you just wanted to shut it off, but hopefully we can make some progress here and make it seem not so bad. So with the example that we ended the last video with, the nice feature of that problem was that we had a very easy time of finding the angle between the two vectors. So in our formula for the magnitude of A times the magnitude of B times the sine of theta to find the magnitude of that cross product vector, we had an easy time finding this angle since the two vectors were in the xy coordinate plane. They were parts of special right triangles. So we found that issue manageable. Now, if we're working with 3D vectors, finding the angle between the two vectors is non-trivial. We can still find it using the dot product, but if we're really not after just the magnitude of the cross product, but we actually want the components, which for many reasons we want the components of a vector, we need a better way to do that. And so to do that, we basically can treat the cross product calculation as a giant distributive property question. So what I have here are two vectors that are defined for us. So we've got the vector A, and so I have it written in component form, ax plus I plus ay j plus azk. So I've just isolated those x, y, and z components, and then I've done the same thing for B. And so if we want to find the cross product, it is defined as follows. So we're going to take the two x components and multiply them together, and then we're going to take the cross product of the vectors I and I. Then we're going to take ax, the x component of A, times the y component of B, and then we're going to take the cross product of I and j. So we can see that here. We're going to do the same thing with the x component of A times the z component of B, and then I'm going to take the cross product of I and k. So I'm basically multiplying the values of the coefficients in front of all of these components, and then I'm taking the cross product to get the vector piece of it for each of these. And so then we do the same thing in the next row, where it's the y component of the A vector times all three components of the B vector with the requisite cross products, and then we do the same thing with the z component. And so the multiplying of the components isn't the problem. The question is, what do we get when we take the cross product of I and I, or of k and I, or of k and k, for example? That's what we really need to know so that we can eventually find what the cross product in component form of these vectors is. And so here we see the results of all those cross products of the unit vectors. And so we can see that I cross I is 0, j cross I gives us negative k, k cross I gives us j, and so on and so on. Now where does all of this come from? Well, it's basically just the application of the right-hand rule. So for example, if I have my x and y axes, and then hopefully you can picture the z axis popping up out of the board, that means that I've got the I vector is running to the right, my j vector is running upwards, and then the k vector is going to be popping out of the screen at us. So if I want to find I cross I, why does that equal 0? Well, think about what the magnitude of the cross product, what the formula for that is. Remember, it involves the sine of theta. Well, if I have the same vector twice, the angle between them is going to be 0. The sine of 0 is the y-coordinate from our unit circle is going to be 0. So I'm going to end up with 0 when I take the cross product of a vector with itself. And so that's why this one is 0, this one is 0, j cross j, and same with k cross k. So we'll start there. Now let's move here to I cross j. So in our diagram here, we can take our fingers and point them in the direction of I. I can curl my fingers in the direction of the unit vector j, and my thumb is going to be pointing straight up out of the board at me. So that's going to be in the direction of k. And it's going to have a magnitude of 1 because the magnitudes of the two original vectors are both going to be 1. The angle between them is 90 degrees, so the sine of that is going to be 1. So I get 1's all the way around, so I get k as my result when I take the cross product of I and j. Now, if we reverse it and I go I cross or j cross I like we see here, now I'm going to end up with the opposite orientation, but still in the k direction. If I take my fingers and point them in the direction of y, and then curl them in the direction of I, in order for me to be able to do that with my right hand, my thumb is going to be pointing down into the board, into the screen, and so therefore I get negative k. So reversing the order of the vectors gives me the opposite value. And so hopefully you can go through the rest of these and see why we get the results that we do. So for I cross k, we can have our fingers pointing to the right here for I. We can curl them upwards towards k, which is coming out of the board at us. Our thumb is going to be pointing down this direction, so it's going to be in the direction of negative j. So again, we can go through and do all that work independently here. And so if we come back to the screen previously, we can now eliminate these three terms. I cross I, we establish as 0. J cross j, we establish as 0. K cross k, we establish as 0. I cross j right here, we know is positive k. This one here, negative j cross I is negative k, and so on and so on. So what we can do eventually is we can combine the pieces that have I, combine the pieces that have j, combine the pieces that have k, and so then we can kind of rearrange that formula there so that now I've got this guy right here as a method for us to be able to find what the components of the cross product are. So I've got ay times bz, so the y component of a times the z component of b, minus the z component of a times the y component of b. Take that result, and that's going to give me the I component of my cross product vector. And then we can do the same sort of thing here to find the j component, and the same sort of thing here to find the z component. So what we can do now is take that formula and then use it to find the components of the cross product of the vectors that we see in front of us. And so I'm going to do just exactly that. So I'm going to take this first part, so I've got ay, so the y component of this first, or the j component of this first one, so negative 5 times the z component of b, so times 6, minus, now it's the z component of a, so 2 times the y component of b is negative 4. And so that taken together is going to give me my I component. I can now do the same thing for j. So the z component of a, 2, times the x component of b, negative 7, minus the x component of a is 6, times the z component of b is 6. So that's going to be times j. And then we can do the same thing for the k component. So I've got ax, which is 6, times by, which is negative 4, minus ay, negative 5, times bx, which is negative 7. And then we'll sneak in a k there. So if I just scroll to give myself a little bit more space, we can now continue on. So we've got negative 30 plus 8i plus negative 14 minus 36j, and then finally plus negative 24 minus 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 means it's going to be negative 35k. And then finally I've got negative 22i minus 50j, and then minus 50 59k. And so those are the components of the cross product of those two vectors. Now, if we had reversed the direction, if we had gone B cross A instead of A cross B, hopefully it doesn't come as a surprise to us that the numbers 22, 50, and 59 would have been exactly the same. They just would have all been positive instead of negative, because the magnitude of the cross product would not be different, but the orientation of it would be 180 degrees opposite, so therefore it would be all positive values instead of all negative.